Hello, and welcome to the final video of the laboratory software. I'm Laz, no surprise there, right? And yeah, so for the last video, kind of like what I hinted at and whatnot, I'm going to be covering the technical term is laboratory compaction characteristics of soils, which is the shorter term is a proctor test. So obviously, kind of like with all the videos that I've done for this series and whatnot, I got to give some clarification for how do we get to the point in order to get the data so we can input the data and then render it into a report in or a format that can be read. So let's give a little bit of background of proctor testing in general, which that's how I'm going to refer this for the rest of this video slash stream. So what a proctor test does is it's collecting soil from, at a job site or, wherever have you may, and it's bringing it back to the laboratory for compaction. Now, the reason why we do that is so we can determine what the maximum density value is, as well as what the optimum percent of moisture is for the test itself. The whole idea for this is to test this, get the data, and with this data, we can reapply it out into the field because, for buildings and structures, you want to make sure that the ground is sound, obviously. So, you know, people will compact the soil. And soil is any kind of naturally existing material. So, where if it's sand or sand clay mixture, silts, fine aggregates, but not necessarily coarse aggregates for this test. There's a completely different test that you would do if you had to do coarse aggregates, which that's anything that's greater than number 4 sieve or 4.75 millimeters big or bigger at that point, if I remember if that's the correct dimensions for the number 4 sieve. Don't quote me on that. I mean, you guys got Google. You can figure it out if you're really that curious to know. So, like I said, you want to make sure the ground's sound. So we'll collect a sample of that, like I said, bring it back to the lab. And there are requirements that the civil engineer will put together in the plans for what that compaction requirement is. And granted, for the material being tested, the material itself doesn't need to be at a certain density. So this is the biggest part where at least anybody new getting into the industry will always think, oh, so we need like 100 pounds per cubic foot or greater. Well, no, it doesn't need to be that. It's what is the maximum compaction value for that soil and or material. Because like with everything else that I covered in this laboratory series, the thing is that you would do all this classification testing to ensure, is the soil being utilized? Is it fit for use in the field? Because there might be certain requirements by the civil engineer where they might say, well, you can utilize existing soils or imported soils for your job site. And, it can't be any greater than, let's say, 10% passing to 200, which, that we covered in hydrometers and washes and things like that. So obviously you wash the soil and then, you see whatever that is. And, granted, if it's outside any of these specific parameters, if it's in the job site plans, mind you, then you're not really going to waste time and effort on running a proctor test because the material is then deemed unsuitable for whatever structure that's being built on it. Most of the time for any kind of structure, there isn't really too much in the way of parameters. If it's roadways usually have parameters of sorts that require the soil classification to be within a certain range and or tolerance. But usually if it's just general building structures and whatnot, the geotechnical report attached with the civil plans might say something along the lines of, you know, the following are unsuitable soils like peat and like fatty clays and things like that. And granted, I know I say fatty clays, and if any of you guys happen to be in a area that's outside my greater state of Florida itself, we don't deal with a lot of fatty clays. So a lot of it is just lime rock and sands. But I know that there's plenty of areas that have fatty clays and whatnot. And it's not that fatty clays are unsuitable. Oh no, they are quite suitable. It just depends on the environment that you're in. And since, for one, we don't have a lot of clays here in Florida, and two, we get a lot of rain and stuff, clays don't like that. So, anyways, I don't mean to get off topic here. So, we'll follow these job parameters, whatever it is, and then we'll do the testing. Like I said, we do this test and we don't know what the values are, you know, until we do the test. It could be 100 pounds per cubic foot. It could be 125 pounds per cubic foot. It really depends on the soil aggregate mixture of the material itself that's being tested, is what's going to deem what your maximum density value is, as well as your optimum moisture. So, with this maximum density value, going back to what the civil engineer has in their plans and whatnot, it might state, well, not it might, it will state a compaction requirement. So, it might say for the building pad footers, it requires a compaction of 98% and or greater. So, that means you have to be within 90% or 98%, excuse me, of that range or greater of what the maximum density is. So if we pull up just a calculator and let's say we got a 112.5, so 112.5 pounds per cubic foot, and we only need 98% of that, then the compaction effort in the field only needs to be 110 or greater at that point. So this is why I state that, you know, this test is important, but this data is mostly used for the field representatives that are from a geotechnical engineering firm to test the ground for density, more so than an actual engineering report to indicate that, hey, everything's good and whatnot with the proctor test. The proctor test just helps reinforce when the field personnel go out and perform density testing. And granted, for the field staff that have to perform this testing, they have multiple methods and ways on how they can perform that, which I'm not going to cover in this. By all means, Google is there. You can look up, soil density testing in the field, and I'm sure that's going to pull up every single possible way that you can properly perform density testing and whatnot. So, this is kind of the whole premise of the proctor test, right? So now let me kind of cover the lab aspects. So kind of like what I said, the field representative, they'll grab us enough sample in order to perform a test. Usually that could be anywhere from like 1 to 2 sandbags or 1 to 2 5-gallon buckets. Bring it back to the lab. We want it air dried. So kind of like what I've stated before, the coined term of air dry is exactly what it is. It just needs to be in the open air drying, or if you want to manipulate it, you can put it in a oven that's no greater than 140 degrees Fahrenheit and or 60 degrees Celsius, but nothing greater than that. And like I've stated before, the only reason why they have a maximum stopping point for that is because that was the highest recorded temperature, well, naturally highest recorded temperature on Earth was 140 degrees Fahrenheit or 60 degrees Celsius. So you do that until the other coin term that I'm pretty sure I said before. You have it out open. Usually it takes overnight, a day. It depends on the material type that you're going to test. And, with that, so with that, with the material, well, depending on the material test, as I'm losing my my concentration a little bit with the notifications here. It just depends how fast it dries. So obviously, if you're working with clays or something, the clays are going to take longer to dry because they hold a lot more moisture than what sands and or aggregates will. So you get it to the coin term of a friable state. So a friable state is where you can get a trowel or a spatula, you can put it through the soil itself that has been air dried and nothing is sticking to the soil. The other term that's coined is SSD, which is saturated surface dry. You're not trying to completely dry out the soil. Okay, if you want it completely dry, that's when you put it in an oven dry temperature, and that's 230 degrees plus or minus 9 Fahrenheit, or 110 degrees Celsius plus or minus 5, which will be for our mystical magical moisture contents, which I've talked about before in one of the other videos. So we do that. It sits overnight because that's just how it is. It takes time for soil to dry, and then we'll prep it. So before we get into prepping it and whatnot, I send that to that person if they join or not. So so now we're going to prep our material. So after our material is friable, air dried, and whatnot, this is when we're going to sieve our material. Typically, for proctor testing, you really only need 2 to 3 types of sieves in order to do this process. The sieve types, you got a 3/4 inch sieve, or a, what is that in millimeters? That's not 0.25, that's 1 inch. Not 12.5, that's a ½ inch. Hold on. Okay, so like an 18.75 millimeter inch sieve, if you're metric. So a 3/4 inch sieve or that. The other sieve type you might use a 3/8 inch sieve. So that's your 9.5 millimeter sieve, and then obviously you have your number 4 sieve, kind of like what I said. That's 4.75 millimeters, and all these are based on openings. So this is to separate out any kind of aggregate that could be mixed into the soil, which once again, aggregate is just a fancy term for rocks. So it's all based upon your testing method, right? Which I'm going to be covering that too. If you guys have seen this series, you already know it's a lot of talking up front, and then we get into the juicy stuff. So you're going to prep your stuff. You're going to get your stuff. You're going to get your sample of soil. You're going to pass it through these sieves and whatnot. If there's any kind of soil clods, like clay clods or anything like that, you're going to make sure that they pass through in the nominal form that is intended to be. So obviously, if it's clay and you have a 1 inch big ball of clay, but it's still brittle or can break apart, you want to break that down where it can pass through its nominal particle size, which will likely pass that number 4 sieve. Okay, so you do all this, you pass it through your sieves, you're going to weigh your sieves individually and whatnot, as well as your material passing your number 4, and that's going to be your actual sand itself that you're going to test itself. You're going to weigh everything, and then you're going to apply this thing called a rock correction factor. Not a lot of people do that, it seems. I know here in Florida, they try to avoid that by recrushing the rock and whatnot. I know every state and region and country does things differently. So, and once again, this isn't to teach you how to do this. This is just to give you background on what is done before we get to the fun meat and potatoes of actually rendering the data. What are we looking at and how does it work? So you do everything depending on your testing method. Is going to depend on your final sample size of your material, because preferably you would want to try to sieve all of your material so you have a representative sample. Granted, you can split it and reproportion your sample itself, and from doing that, you can get a unbiased amount of material. If your field person gets you like 200 pounds of material, which that's good Lord, that's a lot of material to work with. You probably would want to reduce its size. Typically for us, we just run everything through the sieves and whatnot, so we get a good representative sample, figure out a rock correction factor, and then this is where we're going to get into methods and the actual test specifications themselves. So technically for proctor tests, you have two main things for proctor testing. So you have a standard proctor and a modified proctor. So let me explain these differences between the two, because it's all based on what type of compaction is going to be applied in the laboratory. So that's the main designation here. So for standard proctors are for material that's going to be compacted with a 5.5 pound hammer. Follow me here. A 5.5 pound hammer dropped, free fall dropped from a 12-inch distance, and then the mold that you're going to use, which there's only two kinds of molds that you'll use. So you'll either use a 4-inch mold or a 6-inch mold, and it depends on the lettered designation of the method itself that I'm also going to cover here. For your soil aggregate mixture that you're going to have. And that needs to be in 3 equal layers by volume of your mold. So picture this if you can, or you can Google it if you want. So you're going to have a 4 to 6 inch diameter mold, and the height of the mold is probably like about 4.54 inches in height, give or take. There's plus or minuses to everything for these specifications. And then you're going to do that at 3 equal lifts. And then I'll cover more on the size of the molds because, okay, I'm messing up here. I'll cover the number of blows because it depends on the mold size. But before we get into that, let's cover, in case if I'm losing you, let's switch again. So now let's cover the modified proctor method. So kind of like with the standard proctor method, like I said, it's going to be a 5.5 pound hammer dropped from a 12-inch distance. So free fall drop, gravity drop, however you want to say, from a 12-inch distance, that weighted hammer onto the soil inside a 4 or 6-inch mold at 3 equal layers by volume of the mold. For the modified, this we're going to use a 10-pound hammer. It's going to be dropped at a height of 18 inches, and your layers are going to be 5 layers by equal volume, which for the size of the mold itself, it's going to be roughly about 1 inch per layer, or 25 millimeters thick for each layer that's going to be compacted into this mold in order to ascertain this test. Okay, so let's get back to the mold sizes once again. So we got our 4 and our 6 inch. So now I want to talk about number of blows. So the number of blows is always going to be the same depending on the size of the mold itself. So if you are doing a 4-inch mold, your number of blows per layer, whether if it's standard or modified, is going to be 25 blows total. So try to picture this in your head. So try to picture a circular faced hammer that is raised at a height, dropped by gravity, and that happens 25 times for one layer, and now times it by the number of layers that is required. Now, for the 6-inch mold, it is 56 blows total. Once again, following the same thing. So let's say that we're doing a 6-inch standard proctor test. So what that would mean is that we're going to use a 5.5 pound hammer that has a height of 12 inches that can be free-falled onto the soil 56 times per each layer. So if we were to do that, the amount of times that this hammer is going to run, so we do 56 times 3, it'd be 180, or 180, dyslexia, 168 times. And that would be considered 1 point for the test. Now, obviously, if we flip it around, and if we were doing a modified proctor test on a 6-inch mold, remember that's 5 layers. So now we do 56 times 5, that's 280 blows that would be performed, because 56 blows per layer with 5 layers. And that would be considered 1 point. So, before I continue, let me take a sip of tea here. Because you know this dragon's got more to say. Hopefully it's good sleepy time talking from, Laz as he does his TED Talk here. So we're going to go back to the actual testing methods themselves. So now you know what a standard and modified proctor are and what they represent and what actions that are going to be taken in order to compact the material. So the idea of a standard and a modified is how many foot-pounds of force is going to be applied to the soil in a controlled environment. Because obviously we're doing this in a laboratory, so it's a controlled environment. When it's the field, it's not a controlled environment. You can't control the wind, the rain, the erosion, factors of equipment driving over things, if chemicals, so, environmental, efforts, as not to cover it. I think environmental effects is probably the best way to summarize that without going through the whole list and making this even more boring. So we know what a standard proctor is. So we know it's a smaller size hammer, a smaller height and drop, and lesser amount of layers. So that means you're going to have a lesser compacted effect needed for that soil in itself. So it's a lot lesser in foot-pounds of force that's needed for the soil to be considered compacted. And for the modified, it's the other way around. Obviously, we got more layers. We're compacting it more at thinner layers. It's going to make it tighter and more denser. So the rule of thumb here, at least in the laboratory, for all my laboratory people that are out here that does this, you already know your differences by comparison. If you were to run the same material as a standard and or modified, your standard proctor maximum density should be lower than the maximum density for your modified proctor, because there's more compacted effort for the modified. So let's cover into the actual specifications themselves. So as of this time of recording this, you have two designations that you can follow in order to compact your material following standard proctor format. So you have ASTM, and then you have AASHTO. So for ASTM, you got ASTM D698, and then for AASHTO, you got AASHTO's T99. Those are the test method designations given. And obviously you can Google that just to get an idea. You won't be able to see the test methods unless you purchase them. And if you're not in this industry, it makes no sense for you guys to purchase them. And I'm not authorized to share them with you. You have to purchase them yourself. So if you think you're getting on here to get a free test method, that's not how this is going to work neither. I'm not going to single myself out like that. That's illegal. So here's the differences from this. And you're going to see the exact same thing when we cover the modified, because it sounds like everything's about the same, but once again, the amount of compacted effort and force given is what's going to make the difference, correct? Okay, so if we cover ASTM here, you have three different methods that you can do within D698 here. So you have method A, method B, and method C. So method A is where you're going to only use the soil that passes your number 4 sieve, and then you're going to compact it in a 4-inch mold. Method B is where you're going to use a 4-inch proctor mold, except for you're going to use the material passing your 3/8-inch sieve or your 9.5 millimeter sieve, and you're going to compact all that material once again in a 4-inch mold. And then method C is where you're going to test the material passing your 3/4-inch sieve or your what is it, 30, not 30 something, because that's over an inch. Gotta do this again because my memory. So your 18.7 millimeter sieve. I gotta be technical here for everybody because I'm a maniac like that. So anyways, so everything passing your 3/4-inch sieve or your 18.7 millimeter inch sieve, so your openings are that big, that material that is going to pass through, you're going to combine it, and then you're going to compact it in your 6-inch mold. Those are your only three methods that you can perform. These sub-methods, I guess if you could call them, or the method itself, within the testing method, it is either designated by an engineer within the plans itself, or when it's not specified, then it's up to the laboratory itself to determine what is the best course of action, which obviously the best course of action is if you can test it with the rock and everything in there, you're going to get a more representative test for what the field technician is going to deal with in the field. So that's why there's this thing called rock correction factor that I talked about before. Because if you remove that rock out, well, you need to account for it if it is in the field. And that's a whole nother thing that, once again, I'm not really going to cover rock correction factor because it's that gray area that sometimes people do and sometimes people don't, or people circumvent it, or people feel like it's not necessary. And, you know, it's a job site to job site kind of requirement. So now I covered all that. Now let's cover over the AASHTO T99 here. Once again, standard proctor. So this is still following the same format of 3 equal layers with a 5.5 pound hammer from a 12-inch drop. Just in case if I lost you here, because boredom is fun. So for AASHTO's T99 method here, there are 4 different methods that you can do. You got A, B, C, and D for this one, unlike for ASTM where you only have A through C. Now, you're going to see a pattern here really quick. So, method A here, you're only going to use the material passing your number 4 sieve, and you're going to compact it in a 4-inch mold. The exact same thing as method A for ASTM. Okay, let's go to method B. So you're going to use the material that passes your number 4 sieve, which is your 4.75 millimeter sieve here, and you're going to compact it in a 6-inch mold. Okay, a little bit different from ASTM there, because that one they had you use in a 4-inch mold. All right, now let's go to method C. Method C is where you're going to test your 3/4 inch or your 18.7 millimeter opening sieve here, and you're going to compact that in your 4-inch mold. And then method D is the exact same thing as method C, except for it's a 6-inch mold. So you're still going to use your 3/4 inch sieve, so all the material that passes through. So understand, this is a material that can pass through. So if you have big rocks, that's not going to be included in this sample. That's going to be part of your rock correction factor if people want that implemented into the formula of your proctor value. Okay, so it's the material passing that you're going to compact into a 6-inch mold. So, and once again, kind of like what I said, unless if job plans specify which method you're going to do in the laboratory, then it's up to the laboratory to determine what is the best method. Now, I am going to say the reason why the specification has it worded like this is also equipment limitations. It does cost a lot more money if you have machines and additional equipment and the proctor molds and everything in different sizes and variations and whatnot. It costs more on the laboratory to have that, unless if you're a high production laboratory, kind of like where I work at, then you're going to kind of have everything at your disposal where you can do whatever mold or pick whichever method, not whatever mold. But there's some labs that might only have 6-inch proctor molds. Okay, well then, if you're doing ASTM, you're not doing method A or B at all. And if you're doing ASHTO, you're not doing method A or C at all. You're either doing B or D or you're doing C for ASTM. So that's why it leaves it like that. And I can tell you from my years of experience in this, it's very, very rare that job plans and or specifications indicate the exact test or the exact method of the test method that you're going to apply. It might say something like, let's say for roadway base, for example. In the job plans, it might show, okay, your roadway base must be compacted to ASHTO's T99 must attain a compaction percent of 100%. And then that's it. If it states that, then that means we in the lab would have to determine, okay, what method is going to be best suited for that. And like I indicated before, since people don't really like rock correction factors, if you can add the rock back into it, you're going to get a more representative test for when the person goes and does the density. Because if you take all the rock out, it's not going to be as dense, right? Because rocks are heavy. All right, have I lost everybody? Right? Cool. So I know you think it's almost done, but we got to cover modified method. So once again, if you remember, the modified method is you're going to do 5 equal layers. You're going to use a hammer that is 10 pounds in weight, and it's going to drop from a height of 18 inches. So once again, you have two testing methods, one from ASTM and one from ASHTO. So you got ASTM D1557 for your modified proctor, and it has the exact same methods just as D698. So you have A, B, and C, and they are worded the exact same way. So A and B are 4-inch molds, C is a 6-inch mold using the exact same sieves from the number 4, the 3/8, and then the 3/4 respectively from A, B, and C. If you're doing ASHTO, you're going to be doing ASHTO's T180, and ASHTO T180 is following the exact same methods that are in ASHTO's T99. You got A, B, C, and D doing the exact same thing yet again. Method A is a 4-inch mold testing material passing your number 4. Method B is a 6-inch mold for material passing your number 4. Method C is a 4-inch mold passing material from your 3/4 inch sieve, and then method D is a 6-inch mold with material passing your 3/4 inch sieve. Ding, ding, ding. So they're both exactly the same thing. So for your laboratory technician, they don't have to think too hard for what method to pick when they're faced with material that has varying sizes of rock. It's more so what compaction method do they need? Do they need a standard and or the modified? And like I said, they're both almost identical except for how many layers the weight of your hammer, and then the drop height of your hammer itself. Simple. Okay, so now since we covered all that, now it would be time to actually test the material itself. So obviously we've sieved our material over our various sieves. We've determined our test method depending on whatever aggregate that is retained. And we have double checked with the engineer or double checked with the assignment itself to determine is there any specific method given, and then if not, it's up to the technician and or the laboratory to designate this is what we do every time when we deal with X, Y, and Z. Simple. Okay, so now you're going to get your material, and then depending on your specification of choice, well, I say of choice, but that is given to you, will depend on your actual sample size itself and how you're going to test it. So, really quick, because they're both almost exactly the same. So when it comes to ASTM testing methods, regardless if it is standard or modified, you are going to set up points. And the reason why I say set up points is you're going to have separate pans or containers of the soil that you've sieved and remixed together and whatnot. And you're going to set it up in separate points. No less than 4 points. And you're going to see once when I put in my test data here, what I mean by that. So everything must be separated because you're not supposed to retest material. AASHTO, on the other hand, you can have 1 point of whatever weight and or size that is needed per that method itself. So like, let's say if we did AASHTO's T99 method A, it indicates you need a minimum of 7 pounds of material to test. Or what's 7 pounds of material in grams? So 453.6. So, 3,000, so 3 kilos, just a little over 3 kilos. And that's the minimum size requirement. So you can always go more than that. Typically for our facility, we always go 1 pound greater because it's nice just having the extra material needed for testing. That's so you don't have to worry about reprocessing it or resampling or any of this other stuff. That's just a personal thing that we do, but the test method states that. So if you do 6 pounds or 5.5 pounds, it's not right. It's wrong. You need more material. Where if your field technician didn't get you enough or whatever, somebody needs to get you more material of that for your sample because it's not representative at that point. Okay. Test method jargon. Okay. So like I stated, AASHTO, you can reuse the material and whatnot. The big rule of thumb, regardless, is if you have material with aggregate in it, so rocks, right? You don't want to reuse that material after you compacted it. And the reason for that is, well, let's think about it. You got either a 5.5 pound or a 10 pound hammer that is crashing down on that rock at either 25 to 56 times per each layer, depending on the size of your mold, right? And at whatever your drop height is, that rock is going to break after a while. And the thing is once when your rock breaks, it's only going to densify the sample if you keep reusing it over and over again. So that's the only special exception that's given in the AASHTO test methods is if you do have rock in any of the methods, you are to have separate points, kind of like what I stated for ASTM. ASTM, regardless if it has rock or anything, they don't want you to reuse the points because they're afraid that the sand granules or whatever are going to break while it's compacting. And I can tell you personally from experience, and I don't write any of these specifications, I've never seen sand break while running this test. But whatever the reasoning is, that's how it is. That's how you do it if you ever have to do this. So ASTM always has separate points. And, for AASHTO, you can have one big giant point if you want, but if you have rock, you really need to have separate points. So now, here comes the fun part. The fun part on the technician, where you have to develop years of experience here from just running these tests. You have to determine what your optimum moisture is. And then you're going to go 2 to 4% lower than your optimum moisture. So let me explain this here. Before I do, more tea. I'm a little parched. So, determining your optimum moisture. Granted, that's from experience. So, kind of like what I was indicating before, the test itself is going to indicate what your optimum moisture and maximum density value is for a proctor test. So, let's say your optimum moisture is 12.5%. Okay, so you're going to go 2 to 4% below that. Okay, well that's pretty easy to figure out, right? So the tricky part is every soil material is different. So while you might deal with a clean sand frequently, you might tend to notice that it can be, let's say, 10 to 11% would be your optimum moisture, right? You notice that. You notice that, or, your seasoned, experienced soil technician will just say, hey, you want to start adding your moisture between 6 to 8%. So now if you think about it again, that 6 to 8% is 2 to 4% below that optimum. Okay, makes sense, right? So the thing is you might deal with that exact same fine sand from that exact same project used in a different location, and then you do the same thing, and then you realize, oh wow, I'm over optimum moisture, which I'll explain that more when I put the values in and whatnot. So like I said, with your points, you're going to set up these moisture points. You're always going to run a minimum of 4 points, whatever method that you're going to do, or if it's ASTM or AASHTO, and following the same thing, like I said. Where if it's modified or standard, just depends on the weight of your hammer, your drop height, how many layers is it going to be, and then the size of the mold that you're going to use. Okay, so I think with that said and whatnot, let's actually get into the software itself. Good times, right? So let's get into the software. I'm going to show you how it works. So when the lab staff does this, so they'll do it 4 or 5 times. So the point itself, so we'll record the data, perform a moisture content like how I covered and whatnot. So I guess I'll cover over obtaining a moisture content. So technically when we're done compacting it, we'll get a weight of the soil in the mold. We also want to get a weight of the mold itself that we're compacting it into. And then that's going to help us determine our density. And then afterwards, when we compact it, we want to get the soil out of the mold. So usually you can use like a rubber mallet or a dead blow hammer, or if you're working with like clays or something, you might use a hydraulic press to press the soil out of the mold. Because then what you're going to do is with that soil pill, pretty much, you're just going to cut it in half directly, and then you're going to cut another section out of it in the most center portion, and then that's just going to be your moisture content. And just to kind of brush over real quick for how to do a moisture content, that's when you're going to get a pan and or tare that is oven safe. You're going to get the initial weight, which that will be your tare weight that we will see here when I get the software running. You'll get the wet weight of your soil, put it in your pan, whatever size or amount. It depends on your nominal aggregate size or whatever. Typically for proctors themselves, the rule of thumb is if you're doing something in a small mold, so the 4-inch mold, you want at least 100 grams, at least. which more than likely you'll get over 100 grams when you cut that section face out of that soil material and put it in your tear itself. And for your 6-inch mold, you want to get at least 500 grams or greater. Okay, so these are the rules of thumbs to have. So we'll do that. We'll get the weight of the wet soil with the tear itself, record that weight. Then we'll throw it in our drying oven. And like I said, our actual drying oven, that is our oven that is set to 230 degrees plus or minus 9 degrees Fahrenheit, or our 110 plus or minus 5 degrees Celsius. And then depending on your test method, so if you're doing ASTM, ASTM indicates for moisture contents, it must be in there for 12 hours minimum, or you can do consecutive weigh-ins after 8 hours as long as it doesn't change by 0.1%. I believe it's 0.1%. I could be wrong. It could be a little bit bigger. It could be 0.5%. So you could do that if you're like in a rush or something. But for AASHTO though, which that's the roadway methods, it's the minimum's 15 hours. So you ain't touching that till tomorrow, pretty much, is how that works. So there we go, moisture contents. Even though I kind of covered it in one of my other videos, since I haven't done this or talked about it in a while, why not? You know, plus go out with a bang, right? I mean, this is the last video that I'm doing for the laboratory software and whatnot. So we'll got our XP machine here. We're going to log in. I'm going to hope I remember how to log in. And then we're going to use our specialized software here, which this is going to be the laboratory software from the soil mechanics engineering book. I think like the 5th or 8th edition. I've talked about it before. You've seen it and whatnot. So let's see here. I think I have it under my documents still. Hopefully, maybe. No, probably not. See, told you it's been a while. It might actually did program files. No, never mind. I just put it under here. Okay, so that's and that. Okay, I think it's under more soils tests. Okay, so for the example that I have here, I have a proficiency sample that I've done, I don't know, 2018, according to the date here. And this is going to be our mock data that we're going to use in order to see everything to come to life and whatnot, hopefully. So, granted, for any of this, you got to give a description of soil. So a description of soil is you visually identifying it, as well as if you performed any additional classification testing to help determine silts or clays or anything like that. So for this material here, we're just going to say it's a light brown, fine sand with silt. Oh, never mind. We'll say it's light brown because it's going to be a high density. So we'll say light brown. Let's see. Silty fine sand. Whoops, that's not how you spell sand. So, which if you remember from classifications, classification 101 or whatever silly video I did back then, remember anything that is designated as silty fine sand is material that is greater than 12% or 15% if you're doing AASHTO classification. Either way, this stuff was silty because we're going to see a high density and whatnot. So you have a sample number, or sample numbers, whatever is designated by either your company or whatever and whatnot. It's just a additional identifier. Nothing with that. Then we have a location, which that's to represent what this soil represents. So let's say for this example, this sample or the sample itself, this soil is going to be used for, let's say, building pads and footings and like a parking area or something. So it's going to be used all over the job site, But really, there's only just this type of sand, and then there's, you got like tan fine sand or like dark brown fine sand or something like that. Then you could use something like stockpile, because if they have it as a stockpile, they're just going to take it and put it in locations and whatnot. And remember, the location just really more so helps your field representative that's going to be performing the density testing more so than the client and or the contractor that hired us to do the testing. That's that's the whole thing about this. So here we got soil GS. Soil GS means your specific gravity. If you performed a specific gravity, which is something that I talked about before on how to do that, you put your actual specific gravity in here, or you can just, you can always make assumed specific gravities. The test method even covers that as well. You can make assumed specific gravities. And here's the thing. So it is kind of important to have some form of specific gravity, because you can have this phenomenon called zero air voids. So zero air voids is where you've compacted the soil so much, or you were able to achieve zero air voids in the laboratory. And the thing is when you achieve zero air voids, that means you're going to have not necessarily a high density, but you're going to have a density that might be hard to achieve in the field. And the best way to determine that is if you did an actual specific gravity. But if you're kind of spitballing still, you'll still have what's called the zero air voids line that would show up on a proctor graph. And obviously, if your curve is anywhere near there, then there's a chance you might be able to hit zero air voids where, if we have whatever our density value is, so let's say it's like a 117 or something like that. But, in the field, the highest they can get is like a 113, but then they need like 98% compaction. Well, that's out. So if it's close to a zero air voids, then that's where we can either do additional testing like a specific gravity to verify, as well as to not reinstate, but to support our findings with, hey, since we were able to achieve zero air voids, that means there's a possible chance if you put just a little bit more compacted effort in the field, you might be able to achieve the same thing, and then it'll densify very, very tightly and well. Because we do want the soil dense, because once again, we're building structures on it. There's infrastructure going on this. You don't want the soil to be weak and or yielding or anything like that, because that's when, well, the structure is going to fail a lot faster. And hopefully not in a catastrophic way. So, from this, we got our mold volume, which that you get from calibrating your mold, kind of like from everything that I've indicated in this whole thing and realm. Everything in the laboratory must be calibrated, so you know that it's accurate and within the tolerances that it needs to be. Otherwise, you can get false readings. So here you can put in your exact dimensions of your mold. This one specifically is for a 4-inch mold, which is perfect because my test data is going to represent that. Kind of like what I was talking about. We got our hammer weight, 5.5 pounds, and our number of blows, 25. So technically, since we're doing a standard proctor, your hammer weight is going to be 5.5 pounds, and then the number of blows per layer is going to be 25. Since we're doing either method A or C of ASHTO, or method A and B of ASTM. Number of layers, 3. And I can tell you, even though this data is here, this technically doesn't have any bearing for what the formulas in math are. Because as you can see here, it tells you what everything is here, only because this software is from an educational manual for upcoming laboratory technicians and or engineers that are taking their laboratory exams, because engineers need to know how the lab work works. So when they yell at us, when we tell them that's not how it works, they need to know how it works. Okay, so we got our tested by. That's who actually tested it. I'm going to put me down, and in our date, let's use today's date. What was it? 14/26. Okay, so granted, here everything here is reported in pounds and whatnot. I can tell you typically, for all the American people that's going to be watching this and whatnot that loves their freedom units. Typically, we try to do everything in metric. We'll still report values in pounds per cubic foot and whatnot, but it's just so much more accurate if you did it in grams and kilograms. And then you can convert it into pounds and then get your pounds per cubic foot. But everybody's different. Everybody's different. So we're very American here. Fortunately, I've already have everything converted here, even though I've done everything in grams and whatnot. Because as you can see here, moisture content, all that's in grams. You never do moisture contents in pounds because it's not as accurate as metric. That's why. That's why, at least for our facility, we do everything in grams and kilograms when we're performing this test. And you can do conversions. That's why I'm quick with the calculator here. Okay, so we need the weight of our mold. So fortunately, or not fortunately, I already have the data. So the weight of our mold for this is going to be 4.111 pounds. And for our test data here, I've done 5 tests. So kind of like what I was talking about for points. So I did 5 points. So that means, whoops. Well, I don't think it's going to matter that much, but really? Not going to let me click in there and edit it? Okay, that's fine. That's fine. Nothing I can't retype again. And I did it again. There we go. So kind of like what I mentioned, remember, each one of these tests for this specific test method, I used a 5.5 pound hammer at a 12-inch drop, 25 blows, doing 3 layers. So that means I've done that 5 times. So if we bust out our handy dandy calculator yet again, so that means I ran that hammer 5 times 3, 75. So you get 75 blows for each point times 5, 375 times. The hammer was utilized only on this sample, by the way. So this is only one sample. If I had a different sample that, let's say we had just brown silty fine sand, because technically you test any time there is a color change and or a material change. So if we had light brown silty fine sand and then we had that same light brown silty fine sand and let's say rock got into it, so then it'd be with rock, that would be a whole nother test for what I'm doing here. So keep that in mind. That's how people figure out what are we testing and when do we test it. And that's usually determined by the field representative or as well any time when they do their tests in the field, and with them performing their tests in the field, they realize, okay, well, the density is not right. So once again, if I got like a 117 pounds per cubic foot density, and let's say in the field they're getting like 114s, and the roller and the compactor just keeps rolling it and it can't compact anymore, but all they're getting is 114. They're going to recollect another sample because, like I indicated before, we test this in a controlled environment. Out in the field and the open world is an uncontrolled environment. So wind, rain, anything could affect that at any given time, and then we could retest the exact same material again, let's say a month or a week or however much out, and then even though we started with a 117 pounds per cubic foot density, it can easily drop down, like we could get a 115, and then with that being a 115, oh man, check it out, now it's within if they needed like 98% compaction. So that's also the other rule of thumb for all this testing too, is this here is all affected by just the description of the soil itself. Anytime this changes, you get another sample, and we do the exact same test all over again. Okay, so let's get our weight of our sample and mold. So this is after compacting it every single time. So for our first point, we have, what is this? So I try to read my horrible handwriting, 8.011 pounds. And now we start seeing some formulas pop up, or some data formulas. The formulas are off to the side. Look at me, thinking I know what I do what I'm doing, and trying to use English. That's not right. 8.486 is what I meant to type. And then here we got 8.436. Okay, so let's look at the data that we currently have before we even get or put in our moisture contents. So as a laboratory technician, when we perform this test and whatnot, what we're trying to picture in our head is a bell-shaped curve. So if you try to picture a bell-shaped curve right now, you can kind of see it just from the weight of the soil itself. So this is just the moist mass of soil. And as you can see here, it's W2 minus W1. So here's our W2, here's our W1. It's algebra. Here's your math right here. Wham, bam, thank you, ma'am, right? Okay, so as you can see here, we got 3.9 pounds, 4.1 pounds, like 4.3 pounds, 4.4 pounds. Then we go back down to 4.3 pounds. So now try to picture this in a bell-shaped curve, because what we're trying to achieve in the lab is that bell-shaped curve, because within that bell-shaped curve, we're trying to figure out what that maximum density is. So right now, if we look at this, this is probably close to what our maximum density is going to be, which then we calculate that into our unit weight itself, which is in pounds per cubic foot. So this is our wet unit weight of soil. So as you can see, we have these values here, and these are all in pounds per cubic foot, as indicated here. And this is all affected by what is the volume of your mold. This is why it's important to calibrate your equipment beforehand. Granted, we're just going with the default mold value, but this is why it's important, because this density can be affected by whatever your exact volume is going to be. So the way how this is working here is that it is taking this value and then it is dividing it by this value right here in order to get this value here. Okay, cool. So this is us running all of our points, right? But once again, we have our moisture contents. Okay, so you have can number or tear number. You know, we've gone through this before from all of our software programs. Your can or tear number, whatever it is, that's whatever is written on your tear, so you can identify it. Because as you could see, we got 5 tests, so that means we're going to have 5 pans or bowls or whatever oven-safe containers that's going to hold these soil samples and put them in our oven. Well, we got to weigh them again. So we got to know what they are, right? So we just don't want to leave a whole bunch of blank tears in there, and then the next day we're pulling them out and trying to weigh them. It's like, well, I don't know if it goes to here or there or whatever. So that's why it's important to make sure that your cans or tears or however you want to call them are identified and or identifiable. So that's all this is. This has no bearing with any formulas whatsoever. So for this one, I used can number 214. That's just the actual number of what was written on the tear in our pan itself. And let's see here. So we got our weight of can itself in grams, and this one weighed 45.9 grams. And then we have our mass of can with wet soil. So this is where we do the part that I've explained, where we're going to knock out the soil pill itself from the mold by whatever means, and we're going to cut in half, and then we're going to get a cross-section face of that half portion and then throw it into our tear. So you're going to throw it in your tear, but you're going to get the mass of your can as well as the wet soil itself. So you're not going to tear your tear to get only the wet soil. You want to make sure you get your total weight. And the reason for that is in case if, because when soil dries or when it's wet or anything, you want to try to account for any possibility of that change. And this is the best way of doing it. Granted, you could tear it and just have just the soil weight itself, where, you can put 0 here and then 0 your tear on your scale and then put your wet soil in there and then write down that weight. It'll still do the same thing, but it's just a good practice just to do it like this, because you can account for everything. So this one here, we got 160.9, and when it dried, here we got 154.6. Okay, and now let's just rinse and repeat, right? 709. Is this actually going down? It's not. Ooh, this is not enter friendly. Is it tab friendly? No. It's nothing friendly. It's only click friendly, man. Oh. So I can tell you, remember, kind of like what I covered in this series and whatnot, this is just this software is just available for anybody that's training and whatnot. Nobody really uses this software for reporting purposes. I hope nobody's actually using this software for reporting purposes. That wouldn't be great. I just kind of want to cover that right here in case if you're like, wow, this looks very basic and whatnot. Well, yeah, the actual all the math and stuff is basic and it's simple. It's just, if you're like, oh, wow, people still use Windows XP to do. No, it's just because the software is so old. Wait a minute. Whoops, I fucked that up. Okay, so this should be 45.0. Sorry, it's a force of habit kind of thing. Oh, no, it's going to crash. Oh, no. It's okay. I'm a fast typer. See, the good news is, even though it crashed or whatever and whatnot, I don't have to explain everything again. Is the big thing. So, 4.111, 4.111, and I can tell you, like for newer software that is utilized in the laboratory, because you might be thinking like, okay, so if all the weights are the same, why doesn't it just repeat it? And the newer software can repeat mold weights because more than likely you're going to use the same mold. It's not like we're using separate molds for the test. That costs too much money for any lab to have that kind of surplus, because like these molds are expensive because they're engineered for specific things like this. So, what is the lesson learned for tonight so far? The lesson learned is make sure that you actually follow what's on there. Whoops, that's not right. 364, because it'll crash your program. In reality, that really wouldn't happen with like high profile laboratory software, by the way. I mean, if my laboratory software did that, I'd be pretty upset. I would probably never would want to use it again, and I would probably just hand calculate everything and then just write it down on a greasy napkin at the end of the day and have an engineer review it. Let's just say that. All right, so 709. Because technically, whoops, it should be 43, 43.7. So technically, in reality, like how I messed up there, a lot of people are used to that format of writing your it's like this is your first line, this is your second line, that's your last line, even though technically you need this weight first before you can do anything. And that's just kind of been the format for everybody. So that's kind of why that happened, because that's just how it is. Even though logically, computer logically, as you can see, well, yeah, you want the weight of your mold before you do that. Otherwise, if you don't have the weight of your mold, how are you going to calculate it? So, this follows computer logic, which technically, I think a lot of people need to start following, because like everybody's using lab software. Back in the day, I say back in the day as if I've been here since like the 50s. Everything was hand calculated and hand plotted and everything like that. To get a computer was thousands of dollars. If you wanted engineering software, that was tens of thousands of dollars. And yes, while you can make a lot of money in engineering, that's a huge investment to have when you have somebody that's proficient with a protractor and a pencil. It's a lot cheaper to have the protractor and pencil than $10,000 laboratory software. But that was way back in the day. Laboratory software is a lot more affordable now. It's just it depends on what you do. Okay, so while I talk through everything, here we are. So here's our final data right here. So for a proctor in itself, we have all of our wet stuff, and then here's all of our dry stuff. So this is doing our moisture contents. So the way how this works is it your maximum dry density, keywords, dry density, is determined by whatever your moisture content is. So the way how all this works here is whatever your moisture content is, it's going to take that and then it's going to divide it into this in order to get what your dry density is. So that's what these all are at the end of the day. So if I wanted to be fancy, my calculator disappeared. Or is it going to open the okay, well, sometimes it'll open the calculator in XP. It doesn't matter. It's a calculator. So if we wanted to software verify this and whatnot, because things need to match up. Well, technically, if I want to software verify, I need to do all the formulas on the paper, and I'm not doing that. I'm demonstrating software, not how to do everything here. So if we wanted to double check this, so make sure that everything's right or whatever. So here we got 5.80 or 5.8% for our moisture content, and that was from these values here following this formula here. And that's how we got these values from that. So the way how it determines the unit dry weight, because it doesn't specify how it does that, and it's the same thing here, but kind of like what I said, it's just technically taking this divided by this, and then there's your pounds per cubic foot. But that's your wet density, which we don't need to know the wet density. We need to know the dry density for our proctor test. So technically, if we go with test 1 here, so here we got the one, hey, what's going on here? Okay, I didn't need it maximized. So here we got 117.01. And then for that, we're just going to divide that into our moisture content. And I know what you're probably thinking. Okay, well, you convert a percentage into a decimal, because remember, this is in percent. This is all converted. So technically you move your decimal place up to 2 places, which you would still do that. The difference for this testing and whatnot is you need to make it into a whole percent. So making it into a whole percent is where you would add a 1 before that. So if we're doing this 5.80 here, so we're going to do 1.0580. And then as you can see here with rounding, we got 110.59, we got 160.0. It would round to be that. So technically that's how that works there and whatnot. Because sometimes people get really confused about that. So this is how we got all of our points and whatnot. So just looking at this here before we look at the plot, which I'm hoping the plot will work here. We're looking for our highest value. So technically right now at this point, until we look at our plot itself, it looks like test number 4 or point number 4 is giving us a 117.3 pounds per cubic foot at like 11.9% moisture. That would be our data that we would report back to our field representative. So kind of like what I was saying before, just with this in general, if they needed just like, let's say 95% compaction of that, so then it'd be 117.3 divided by 0.95, it's 95%. So that means in the field, they need to have at least 111.4 pounds per cubic foot and or greater. That's how all that works. All right, so let's see if the show plot's going to work. I hope it's going to work. Okay. Perfect. So our show plot's going to work. So technically, this is what is... Can I make that bigger? That's perfect. So this is what's actually in a proctor report. Besides the location and everything and whatnot, you'll have this graph here. So as you can see with the X part of the graph, it's your moisture content. And, here's 6, 8, 10, 12, 14. And, you can change it to whatever in the world that you want or, however your software behaves and whatnot. But it always does it in some shape, way, form, and or fashion of like this. And then obviously on your y-axis, you have your dry unit weight, which this is shown in pounds per cubic foot. You could do me, I almost said meters squared. Like you could do like newtons, and there, you know, I don't I don't know all of the metric densification things because we're still in America. You know it. God forbid if we reported something in megapascals, somebody would lose their mind instead of psi for force. So here's our curve here. So technically, the way how the curve works is each one of these is our points. Boom, 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 boom. All five of them. And you can see it following the same thing that is done here. If we can, does that actually clear it out? I can't have two things open at once. Hold on, I wonder if I can move this off to the side so I can pretend I'm demonstrating a point. Here we go. So as I'm trying to demonstrate a point. So as we look right here, so here we got 108, 112. So here's our 110. Here's our 114. Here's our 116. Here's our 117. And then here's our 113. And then obviously with our moisture and whatnot. So even though we know the highest point is here, which we can see right here, and this curve isn't necessarily it has to be a best fit curve or it has to connect all the points. Technically, if you were to hand plot this using like a French curve, you would, most of the time people will connect the dots. But obviously for like laboratory software, it'll do a best fit curve because your curve needs to be a bell-shaped curve of some sort. It can't be anything weird. Because if it's anything weird, then you need to rerun a point, or maybe you got to rerun the sample. You don't want your curve where it's off the scale shown here. So if we have points that was so jagged that went up and went down off the scale, you can't really report that. You need to correct the points or rerun the test or something like that. But that's internal things that you have to do. So technically, even though you're thinking, okay, so here it is right here. This would be our maximum dry density and our optimum moisture. But technically, it's your highest point of your curve, which would be here. So if we were to plot this, we're probably about, so if this is like 117 here and this is 116, this could be like either, if we kind of minimize it just to see and whatnot, because usually with more sophisticated programming, it'll pinpoint right there what the highest point of your curve is and report it as such. But since this is just practice testing software, it's just to, oh, cool. So that's how a proctor curve works. So that's how it should look if I had this data, or just, it's just a general go by for anybody that's learning it or getting into the industry and whatnot, or becoming a, not a civil engineer, but like a geotechnical engineer or a structural engineer or any of the sub engineering degrees that you could get in this industry. So technically you're going to get it at your most highest point here. So even though we got like 117.33 that's over here, our highest point of our curve is right here. So at least trying to eyeball it here. So if that's 117.3, I'd say this might be more close to maybe 117-ish, since 116 is here. So we could say that's probably maybe about 117, and then looking at our moisture here. So here is going to be 11. That's dead set right here. So it's going to be more than 11. So we could probably say it could be maybe 11.3, 11.5, give or take. So it'd be 117 at like, let's just say 11.3% moisture would be your optimum moisture. So, cool, right? That pretty much covers everything. And it's true, it does cover everything. But now I'm going to cover an important aspect, proctor curves. Here's the important aspect that I think everybody has forgotten over the time. Everybody just wants that number. I need to know that maximum density number and whatnot. Okay, cool, perfect. Yes, here it is. This is your maximum. But as you can see, we got a curve here. And the reason for that is let's say your field representative is out testing and they got, I don't know, let's say a 115. Yeah, let's just say they got like a 115 density. And here we know we need a 117, right? So, and let's say they needed well, 95% well, not 90. Well, actually, yeah, no, that'd still be it within. Anywho, regardless of the compaction requirement, the important thing here is that this graph here is to help with a moisture gradient. So, okay, so let's say they got that 115. It's still 95% compaction. Okay, they are within. But let's say the moisture is more close to 14%. Okay, now I'll tell you, generally speaking, and granted, it is going to vary from project to project or what location you're at, where if it's, outside the United States or a different state or anything like this. There are some projects that will specify you must be within your, you must be within your compaction range, but within a moisture range as well. So, and typically they might say 2 to 4%. So technically, if you had a 115, if you were on a job or a project that required that moisture to be within 2 to 4% of whatever your optimum is, and you're around 15%, okay, cool, you're at density, but it's too wet. That means it needs to dry out. And this is where this curve is super, super, super handy, especially when you're out in the field. And almost nobody uses it like this. You got to see wherever your moisture is at and figure out wherever it goes. Because technically, in the field, if you've played around with soil, dirt, sand, if you've gone to the beach or anything like that, or just made mud pies growing up, however, I'm pretty sure you've noticed if you add water to soil, it denses up. It holds together a lot tighter. But then if you add too much water, that's when it's just in a liquid state or just mud. It's not necessarily holding together as well as, sand that is dry, sand or clay or anything that is dry. And that's what's important about this graph here is to determine your moisture. So let's say for an example, I go out in the field, I'm doing a density test and I'm getting a 108. Okay, well, obviously for it to pass, we need a 111 pounds per cubic foot or higher. Okay, so I'm getting a 108, so we're not there. That's okay. So that means we just need more compacted effort. But let's say I get that 108 and we're at like, what is that? 4.7% moisture. Okay, well, with the help of this graph, I can clearly see, okay, we need to add more water. Because if we add more water, we'll start to densify. So, if we get it up to like 6% and then apply the right amount of compaction or the compacted effort that was attained in the lab, then you could be right here where now it's, I know it doesn't help because of how big the gap is, but we would probably be within the range that we need to be within because it's only, what, 111.4? So you could probably be about a 111.4 there because our first point was 110.6. And then our second point right here, here's our 114.8. So, here is our lowest denominator here that's going to get us closer to wherever we got to be. So that might be more close to 111. And it's like I said, that's just with us right there on the spot doing the density tests. Because when we do the density tests in the field, we will have a natural moisture content of the soil itself. So that helps us determine, hey, we need to add more water. We need to add more water, and then that's going to densify the soil more. Because, we could say, okay, well, you can just keep rolling it with your compactor or your steamroller or whatever that you're going to use. Well, the issue is if the moisture's here, it's not going to densify anymore, because if we were to run points for everything, it's just going to curve. So technically you could just kind of almost follow this trend line here, and you could see, okay, so if I'm at like the 108 here, and kind of like what I said with the 4.7, that's probably more close to 4.5. Yeah, we're close to it. That's why these are so important, but it's something that people, or at least the field person, doesn't understand how to use this, when this is like the most valuable tool in their toolbox to help the contractors to get it up to here, because it could be a moisture issue. And it could be the other way around, where, hey, we did a test or whatever, but we're at like 20% moisture. Okay, obviously on here, 20% is off the scale, but if we keep following this, and let's say like 20% is like here, okay, well, we see 100 pounds per cubic foot here. And if we had 20%, because let's say it was a heavy rainstorm, or the soil's pumping or retained a lot of water or something, okay, well, hey, your stuff's way too wet. Because if I was getting like a 104 at like 20%, even though 20% is around 100, okay, well, it is densifying because of the water, but it's never going to get there because it's too wet. So obviously they have to dry it out in the field. And by drying it out, that's really, they just got to wait for a sunny day and, try to mix the soil and whatnot and let Mother Nature do the work. And hopefully it's not a rainy day. That's how we deal with that. There is no like portable ovens that you can apply in the field or anything like that to dry the soil to get it back to where it is. But this is the important value of having this proctor curve. So there's my tangent TED talk for the day right there, is, the importance of this. At least having this here, or having this for the field representative. And I can't tell you how many times I've seen it where either they don't have this, all they have is just the maximum density number, just so they could do their test, say, okay, pass or fail. When really we're there to help the client and contractor. Okay, well, we need the soil densified to this compaction percent. And if the material is getting a 117 and you're getting a 108, and let's say you're here for moisture, even 10%, then hey, you could do more compacted effort and you can get there with that. But once again, it also depends on that moisture percent tolerance, if the project has one. Because, like I said, if we're here, but it's plus or minus 2%, it's 11%. Okay, well, you can't be any less than 9%. You can't be any greater than 13%. So, and granted, we don't deal with it that much on our side of the world. And I think the only reason why we don't deal with it that much, having actual moisture percent tolerances, is because of the type of soil that we have. We have a lot of sandy, granular material. So when it gets wet, the water can percolate through. Unlike for clays and whatnot, it likes to retain water. And, obviously, if the clay has more water, if you've ever played with Play-Doh or clay or anything, you notice if you add more water, it becomes more pliable and more thin. And, that's also another thing you don't want your building on, is something that can change, because then your structure becomes unstable. But yeah, there we go. That, everybody, is laboratory compaction characteristics of soils, otherwise known as the proctor. And that pretty much wraps up this series for laboratory software. Yeah, I don't know if didn't really get a lot of questions or concerns or anything like that. which is fine. You know, I just like streaming this and whatnot in case somebody would like to interrupt me or just say, "Laz, you're a fucking lunatic, man," and that's okay. That's the reason why I've been doing this for as long as I've been doing it. But once again, I hope you enjoyed this series. Nice little kickoff and send off as well, because obviously by July the website's going to be down for an undisclosed amount of time. So it's kind of nice to wrap up this series in time before, you know, I do my transitional period of getting everything all set up and all fancy and whatnot. So yeah, I'm happy I was able to do that. Hopefully I didn't bore you guys too much and whatnot. You know, if you stuck it all the way to the end of the video portion, that is, you know, I hope you liked it. Definitely, you know, if you have any specialized comments or anything and whatnot, you know, I'll answer them to the best of my ability. Remember, I'm not an engineer. I'm just a well-seasoned, experienced laboratory technician that's been doing this for 19 years now. And, you know, I just had the opportunity to get my hands on this software. Obviously, since we're at the end of this series as well, I guess I'll consider if I'm going to post the software or not. If there's interest, I don't mind posting it. Everything that I've featured here and whatnot, it's like I said, from the first part of Geosystems, it's my old company that has gotten acquired, and it doesn't exist anymore. So the licensing and everything is gone, and there's really no repercussions. And from how old the software is compared to the new stuff, even if you thought about, well, I'm going to open up my own geotechnical engineering firm, well, yeah, I wouldn't recommend using that software because it's dated and it doesn't do everything that the new software can do. But hey, you know, everybody can do whatever in the world that they want to do. So I do want to kind of add in here, just as a side tidbit, if I do happen to post this software, it's not going to be anytime soon. It's going to be when the 3.0 site is up, because I'm not posting any new software or anything. The only new posts that I'm doing on my website are only video content like this as a kickoff to say goodbye to it as we go into the new. But anyways, that's enough of me talking and rambling. I think I've only been doing this for well over 2 hours now, and that's okay because I don't mind talking. So yeah, I don't know. I guess that's it. That's the end of this video. Yeah, I hope you guys enjoyed, and I'll see you for the next project that I do. Don't know. I don't know if it'll be a let's play or something special or whatnot. I know I don't have any software right now to test or whatever, but you know, obviously I'm open to suggestions and ideas too as well. You know, you can leave that in the comments below in the video or message me or, you know, get a hold of me. However, all right, guys. I'll catch you next time. See ya.